All right, tonight what we're going to be talking about are empirical formulas and molecular formulas. Empirical are the simplest whole number ratio of elements in a compound. So if I had, for example, H2O2, this would be considered the molecular, which we're not into yet, but the empirical is if I can reduce this at all, that would be the empirical. So because I could divide both of these subscripts by 2, my empirical formula would be HO. So my empirical formula is the most reduced. Now, not all formulas can be reduced. For example, if I had water, which is H2O, its empirical, even though its true formula is H2O, its empirical formula, which is the most reduced, is also the same thing. And that's because you can't reduce 2 and 1. So sometimes the empirical formula is its true formula. Now, a lot of times why you do use empirical formulas? Well, the reason comes about because the machines that we use as chemists oftentimes spit out information such as this substance is 40% calcium and 30% oxygen and 20% hydrogen. And from that, we have to be able to develop a formula. So there's a different steps that you take when you're given these percentages or a certain amount of grams in order to figure out what its true formula or simplest version formula is, either the empirical or the molecular. And right now we're just going to be focusing on the empirical. And all you have to do are follow these steps every single time and they work. And once again, the reason why we do this is because the machines that chemists often use give their information out in the percentages. They can analyze it based off of percentages. And from there, we can calculate the corresponding elemental formula or the chemical formula. All right, so what you're going to do is you're going to follow those steps. And so when you read this, it says a sample with a total mass of 24.975 grams was analyzed to have 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. So determine the empirical formula. The first thing that you need to do is if you're given percentages, you turn them into grams, and if you're already given grams, keep them. Then what you need to do is convert every single element into the amount of moles for that element. So I'm going to convert, first of all, calcium. So I'm going to do 13.5 grams of calcium over X moles of calcium. And I know that that is proportionally going to be the same as its molar mass, which is 40.1 grams of calcium for every 1 mole. Once again, we are just dealing with proportions. When we solve this, we get calcium would have 0.3367 moles. Okay, now let's do oxygen. So oxygen, we knew that it had 10.8 grams of oxygen. And we need to figure out, once again, how many moles that is. So over X moles, we know that oxygen is 16.0 grams of oxygen for every 1 mole of oxygen. So when you cross multiply this, you get 0.67, that's a 6, 5 moles of oxygen. And then now we need to do hydrogen. In hydrogen, we have 0.675 grams. And we need to figure out how many moles that is. And I know that there is 1 gram of hydrogen for every 1 mole of hydrogen. So when I cross multiply this, I get 0.675 moles. Okay, the next step is divide by the lowest number of moles. So calcium is 0.3367, oxygen 0.675, and hydrogen is 0.675. So the lowest number is actually going to be my calcium amount. So I'm going to divide all of these moles that I just solved for by the lowest amount, which was 0.3367. So I get 1. When I divide this one by the 0.3367, I get 2. And when I divide the 0.675, once again, by the lowest, which is 0.3367, we get 2. So these are my ratios. So what does that mean? Well, it becomes Ca1. And then my oxygen was 2. So I'm going to do O2. And then my hydrogen was also 2. So it was H2. And this would be my empirical formula. So Ca1O2 H2. And all you have to do is continuously do this for every single empirical formula calculation. All right, now empirical is the most reduced. Molecular is the actual number of each atom in a compound, as I was talking about before. Sometimes it's the same as the empirical as or it's multiple of the empirical to get to your molecular. So for example, if I had H2O, H2O, which is water, is both the water's molecular formula and its most reduced of empirical. Whereas on the other side, if we had hydrogen peroxide, which is H2O2, its empirical formula, which would be the most reduced, would be HO. Its molecular formula, which shows you the true number, would be H2O2. And therefore, it would be a multiple of, its molecular formula would be a multiple of 2 of its empirical formula, because all you would have to do would be multiply the subscripts by 2 for HO to get your H2O2. All right, so identify which formula would have the empirical formula. So if CH4, now this would be C1H4, and this would be C2H8. So the most reduced, which is the empirical formula, would be C1H4. Now if I look at this guy, C6H12O6, I know I can divide both of those by 6. So that would not be an empirical formula, where CO2 is the empirical formula because I have subscripts of 1 and 2, and I can't reduce that anymore. The next question, give 2 molecular formulas from the following empirical. So this would be the most reduced. So for the first one, I'm going to multiply those subscripts by 2, just because you can multiply them by any subscript you want, so, or any number you want. So it would be C2H4, and this would be a molecular. The next one I'm going to do is, let's say, just 10. So I'm going to multiply CH2 by 10, so it would be C10H20. So these would be molecular formulas of your empirical formula of CH2. All right, for this drawing, what would be the empirical and the molecular formula? Once again, the molecular is its true formula, so I think it's actually the easiest to do that. These guys are the hydrogen that I'm coloring in brown, and then the carbons are blue. So if I do my counts for this, I get C2H4. I always recommend finding out the molecular first and then doing the empirical. So if I then do look at this, C2H4, I can reduce both of those by 2. So my final formula for my empirical would be CH2 or C1H2. And then this shows you, number 4 shows you how the molecular and empirical can be the same, and yet it can also be multiples. So for water example, the multiple is 1. For sodium peroxide of NaO, that multiple would be 2. So I had to multiply its empirical by 2 to get to Na2O2. And then the cyclohexane, all I had to do was multiply this guy by 6. So its multiple would be 6 to go from my empirical of CH2 to C6H12. All right, as with the empirical formulas, the molecular formulas follow the same pattern over and over again. So first you're going to add up the molar mass of the empirical formula. If you're not given it, then you have to find it first, which means you have to follow those previous steps on the previous slide before you even start step 1 of the molecular. Then you're going to take the molecular mass and divide it by the empirical molar mass, round this to the whole number, and then multiply it out. I think it's a lot easier just to do it than to kind of read it and try to figure out. So an oxide of chromium has an empirical formula of CrO3, which is really nice that they actually give us the empirical formula. It's always nice when they give it to us. It eliminates a lot of steps. And a molar mass of 200 grams per mole. What is the molecular formula? So the first step that you're going to need to do is figure out the molar mass of your empirical. I was given my empirical, which is CrO3. So I'm going to do 52 times 1. Because its molar mass is 52.0. Sorry, I should have a 0.0. Plus, there are 3 oxygens, each with a mass of 16.0. So my molar mass of my empirical formula is 100 grams for every mole. All right, the next step is to take your molecular mass, which is this 200 grams, and you're going to divide it by your empirical. So I'm going to take 200 divided by 100, because that's my empirical, and I get a multiple of 2, which means that there are 2 of these guys of my empiricals in my molecular. So then what I'm going to do is multiply the CrO3 subscripts by 2. So I end up with Cr2O6. Okay? A way to check this is to add up the molar mass of this guy, which is 2 times 52.0 plus 6 times 16.0 0.0. And if you get 200, which you do in this case, then you know that this is the true molecular formula. If you don't, then you know something's wrong. All right, in this example, we don't give you the exact empirical, so the first thing that you're going to need to do is find the empirical formula so that you can figure out the molar mass of your empirical. So once again, you're going to do the same steps that you did for the empirical formula. When they give you percentages, just to let you know, all you do is change that sign into grams. So instead of 80%, I'm going to say 80 grams of carbon. Okay, that is proportionally, I want to figure out how many moles that is, where it's proportionally the same as the molar mass of carbon, which is 12.0 grams for every 1 mole of carbon. When I cross multiply, I get 6.67 moles of carbon. Right? Now I need to do the exact same thing, but in this case for hydrogen. So I know that it's 20 grams of hydrogen, and I want to figure out how many moles that is. So I'm going to set that equal to my molar mass of hydrogen, which is 1 gram for every 1 mole of hydrogen. So when I cross multiply this, I get 20.0 moles of hydrogen. All right, the next step is to divide by the lowest number, which in this case is the 6.67 moles of carbon. So I'm going to divide both by 6.67. For carbon, I get 1. When I divide 20 by 6.67, I get 3. So now I know that my empirical formula is C1H3. So now I'm ready to actually calculate start doing the molecular formula calculations. And the first step is to find the molar mass of CH3, which is your empirical formula. So we're going to do 1 times 12 plus 3 times 1, and we get a total molar mass of 15 grams. The next step is to take your molecular formula's mass, which is 90, divide it by my empirical formula mass, which is 15, that I just figured out, and that equals a total of 6. So now I know that there are 6, or there's a multiple of 6 of my empirical formulas in my molecular formula. So what I'm going to do is take my empirical formula of CH3, and I'm going to multiply those subscripts by 6, so I get my molecular formula of C6H18. Once again, it's a smart idea to actually calculate this molar mass just to make sure that you're right. So you're going to take 6 times 12 plus 1 times 18, or 18 times 1, and you do end up getting 90. So I know that, my molecular formula of C6H18 was correct. All right, hopefully you have a basic understanding of empirical and molecular formulas. Remember, empirical is your most reduced, molecular is your true formula. Sometimes they're the same, but most often they are different. Have a good evening.